All right, let's take a look at integration by parts. So what we're going to do comes from our product rule for derivatives. So if I have two functions, u and v, that are both functions of x, hopefully we recall from differential calculus that the derivative of u times v would be u times the derivative of v plus v times the derivative of u, right? And because we have the chain rule, right, both u and v are functions of x, we have to be careful. So I've got u times the derivative of v plus v times the derivative of u. So I can think about this as like uv prime plus v u prime, okay? The derivative of v with respect to x, just thinking of it as v prime. Okay, so if I rewrite in such a way so that I can integrate both sides with respect to x, so with respect to x, that's going to yield that u times v is equal to integral of a sum is the sum of the integrals. So I'm looking at u v prime dx plus the integral of v u prime dx. All right, but v prime times dx is really just dv, and u prime dx is really just du. So we have that uv is equal to the integral of u dv minus the integral of v du. And so all I'm going to do here is rearrange. And I'm going to write this as the integral of u dv is equal to u times v minus the integral of v du. And this is the form that we normally think of our formula for integration by parts. So let's take a look at an example. And we're going to start with a simple one, and then I'll throw some more complicated ones into the next video. So a simple example, and often usually when we do integration by parts, it's because we have a monomial times a function that doesn't disappear when we differentiate it. So something like an x to a power times an e to the x, sine x, cosine x, something like that. So our first task is to identify which part of this is u and which part of this is dv. And whatever part we choose as our u is going to get differentiated, and whatever part we choose as our dv will get integrated. So in making the choice of u and dv, well, ultimately we want to have something that we can integrate. So we don't want to make this expression any more complicated. So we want to choose our u and dv in such a way that we're simplifying. So in the case where I have x to a power times e to the x, sine x, or cosine x, typically I'm going to choose the monomial as my u, because when I differentiate that, it's going to knock it down a power. And then it doesn't matter if I differentiate or integrate e to the x, it's going to give me e to the x. Same thing if we had a sine x or cosine x. Those are just going to alternate between sine x and cosine x, plus or minus. So I'm going to choose e to the x dx for my dv. So now I'm going to find the differential of this one. So my du is just dx. That's pretty straightforward. And then I'm going to integrate this thing. And so my v then is going to just be e to the x. Notice that I'm not really concerned with my constant of integration here. I know that when I do my original integral of x e to the x dx, I'm going to have a plus c at the end. The plus c that I would get from the integral of e to the x dx is a different plus c, and we are not concerned with that right now. We're just going to add a single plus c at the end. Okay, so now using my integration by parts formula, we saw that the integral of u times dv is equal to u times v, so our u is x, our v is e to the x, minus the integral of v times du, so e to the x times dx. And that's a super simple integral to compute. So we have x e to the x minus e to the x. And this is where I'm going to add my plus c. And so that's our final answer. And we'll look at some more complicated examples in the next video.